All right, so is this point on this line? What do I need to do to figure that out?
You have to.
What? Ian, my man, what's going on, dude?
What's going on?
What you got for me?
Substitute the x and y into the x and y, so 3 and minus 2.
Okay.
So it'd be minus 2 equals 2 times 3 minus 8.
Very good. And now, Cameron, what does that do for me?
You have to then just solve. I guess. Well, you have to multiply the 2 times 3 and then subtract 8 from it.
So if
And then
this point is on there, I should get a true statement when it's all said and done.
Yes.
Right?
Yes.
So 2 times 3 is 6. 6 minus 8 is?
Negative 2.
Negative 2. So I get a true statement at the end, so then that tells me that point is on that line. All right? Does that make sense to everybody? That's all you have to do is substitute in the x and the y, and that'll tell you if the point is on that line. All right, very good. Slope. Find the slope of a line passing through 3, negative 2, and 2, negative 1. So 3, and that's not right. I said that wrong. 3, negative 9, and 2, negative 1. How do I determine the slope? Someone else? Yes, Aiden?
You'll just put the y's in the top, so y2 minus y1 divided by, and it would be x2 minus 1.
Y2 minus Y1, X2 minus X1. What's another way to say? Does anybody remember how we, like the quick way we say slope is equal to blank over blank? Who said that? Piper, very nice. Rise over run. How much is your graph rising as you look at your graph from left to right over that run, right? As you go from left to right, how much does it rise? So that's the rise over run. What's the symbol whenever we're writing an equation of a line that we use? What variable do we use to represent slope? Yes. Elm, right? So elm for slope makes perfect sense, right?
Yeah.
Yeah, right, totally. This is just the difference of the y terms, right? Y2 minus y1 over the difference of the x terms. And you could actually do those in any order. You could do the y1 minus y2 over x1 minus x2 as long as you put the same coordinate, like use the same point first, right? So this could be x1 and y1 here, and this could be x2, y2 here, or you could switch it around. The point is you're finding the difference between the two. And so if we do it like this, then it'll be negative 1 minus 9, minus a negative 9, sorry. Negative 1 minus negative 9 over 2 minus 3. And so negative 1 minus a negative is going to be negative 1 plus 9. So that's going to be a positive 8 over
Negative 1.
negative 1. So our final answer is
Negative 8.
negative 8. Wow. I feel like I have to give the whole class a +1 on that, but it's mainly this area here. So was it you two ladies that I heard yell it out? Did I have anything from you back here? Okay, all right. So thank you for your honesty, Annalie. We're going to write your name on the board just because you're being honest. Good job. So negative 8 is our slope. Everybody agree with that? Mm-hmm. Okay. What is the general form of a line? What a slope-intercept form of a line? Let me say that. Who can give me the equation? Somebody new. Yes.
Y equals mx plus b.
Y equals mx plus b. Everybody agree with Cal?
Yeah.
Yes, I like that answer. Y equals mx plus b, where m is our slope. Someone whose name's not on the board. What's the b?
The b is the starting point.
B is y-intercept.
The b is the y-intercept. Thank you very much. Joey got it. What did you mean by, I wrote Joey, I meant the right y-intercept. Sorry about that. What did you mean by the starting point, Jackson?
It's like how the height and like where to start the line.
Maybe where to start it if you're thinking about starting it from the y-axis, right? So if you're thinking about it that way, but it's a line, so it actually goes through that point, right? It doesn't really have a starting point because it's going in the same. It's got 2 arrows on the end, so it's just going, right? That's okay, Jackson. You put yourself out there, bud, and you were assertive when you said it. There was no doubt, right? It's like that's where you started.
Yeah, I mean it's just.
It makes sense to you,
I've
right?
graphed so many of them.
Yes. Okay.
It's like,
Because that's what he does in his spare time. he drafts lines,
I
right?
actually do.
You should confess that to the class.
I shouldn't. I didn't.
All right, so y equals mx plus b, very good. So if it says find an equation of a line that passes through a point 3, 4. All right, let's try to do this without looking at the book. All right, nobody look at the book. Eyes on me. I feel important when you guys do that. That's like you're hanging on every word, right? Make sure y'all still looking. David's not looking. David, me, come on, man. I'm not feeling important when you're not looking at me. Y-intercept of 5, all right? Equals 5. You agree with that, David? Okay, now just make sure you're paying attention. So, what in our equation of a line, where do I put the 5?
B.
Where B is, because B stands for y-intercept, duh, just like m stands for slope. Makes perfect sense. Y equals mx plus 5, right? How do I find, but this is the equation of our line, and the equation of our line has the y and the x still in it, right? So how am I going to find, what I need to find in order to give the equation for the line is my m. How do I find that?
Well, you need to plug in the y and the
I
x.
plug in that point that I know is on there. Is that a 3 and a k? What is that?
I think it's supposed to be a 4.
It's supposed to be a 4? Wow. Okay. This is probably, you know what, this was probably the point at which David wasn't making eye contact, so I wasn't feeling very important at that moment. So, since I'm picking on David a lot, I'll write his name on the board. Alright, so we're just going to plug those points in, right? So we have 4 equals m times 3 plus 5. Everybody good with that? Alright, so we're going to move our 5 to the other side and make it a negative 5. So it's 4 minus 5 equals 3m. We're going to write that like that. Negative 1 equals 3m. We divide both sides by 3, so we can get rid of the 3 here. And so m equals negative 1/3. Yeah, you guys like that? Okay? So now we're just going to take that and plug it back in our equation right here. And so the equation of our line is y equals negative 1/3 plus 5. Okay? X, sorry. Negative 1/3 x plus 5. So that's the equation of our line. There's one other way, and we're doing this review because you're going to have problems like this, right? I mean, not in the book. You're going to have problems like this in general. One day you're going to have 2 points. You're going to be like, what is the equation of a line, right? Somebody's going to ask you, some random dude on the street. I'll give you $100 right now. That's happened to me like 3 times last year. No, you're going to need it for your problems in the book, right? So the last scenario is, what if I give you 2 points? And I said, find the equation of a line, right? So just because I don't want you guys to look in the book, I'm just going to make up my 2 points. You didn't see that coming, did you? All right, so I'm going to say my 2 points are 2, 4, and 5, 6. That's probably not going to turn out well at all. Those are going to be really wacky. Let's make it a little bit simpler, all right? Because I can't multiply very high. So we're just going to do 1,
Negative 2.
1, negative 2? Okay. All right, we'll do that. I like that. Nice small numbers. How are we going to find the equation of our line if all we have is 2 points? Yes, you got an idea, Ian?
Either rise over run.
Rise over run will give us the...
y2 minus y1.
No, I mean, what is that called, though? Rise over run is the
slope.
The slope, right? So y2 minus y1. Now, like I said, it doesn't matter which point you start with as far as your y2, but you need to use the same point for y2 and the same point for x2, right? So which one do you want to start with?
Minus 2.
Minus 2? All right, so we'll do minus 2 minus 4,
4.
right? And then what's the bottom?
1 minus 2.
1 minus 2. So you guys see what he did? He took this y-coordinate minus this y-coordinate on the top, and then this x-coordinate minus this x-coordinate on the bottom, right? And so that gives us a value of negative 2 minus 4 is negative 6. All of that over 1 minus 2 is a negative 1. So our final slope is 6. It's a nice even number. Good. Who picked those points? Did you pick those points? The second point? Was that you? Nice job. Well, we'll see. Let's see how the B works out. Right. So far, though, we're looking pretty good. So this is our equation. Y equals mx plus b. So we're going to plug in what we know is our slope. Y equals 6x plus b. So now we've got the same problem that we basically did last time. Right. We've got the equation for our line now. We just have to plug in a point. Which of these points, this is important, which of these points do I have to plug in? That's so funny, you're all scared to ask. It doesn't matter, right? Either one, you can use either point because we know both of those points are on the line. As long as you have a point that you know is on the line, you can use any of those points when you plug it in. Okay? Is that clear? So it doesn't matter. We can use whichever one we want. I would use the one that's going to be the simplest math, right? So let's do -2. We're going to pick this point. -2 equals 6 times 1 plus b. And then we're going to have -2 equals 6 plus b. We're going to subtract the 6 from both sides. We're going to -8 on this side. And we're going to say b equals -8. All right? So somebody that hasn't got their name on the board yet, what would my final equation for my line be? If I know all those values. Brittany.
Y equals -8. No.
Nope.
Sorry.
What's next? Y equals, what was our slope?
Oh, the slope was -6.
Was it -6?
6. Just
Right here.
plain 6.
Right here. So slope is 6, 6x. Now our y-intercept is
-8.
-8. Exactly. Does everybody agree with Brittany?
Mm-hmm.
Okay. You write down Brittany's name correctly so it doesn't look like my 4 did a minute ago. Brittany. All right. Good. So that was a super fast speed through algebra review that was really all about using lines and understanding the slope-intercept form of a line. Does that seem familiar to you guys, even if you haven't seen it in a while? All right. So you can go through. You're gonna get an opportunity to practice that, and I hope someone comes up to you and goes, "Hey, here's $100. Got 2 points. Need a line." All right. Maybe that'll happen to you next week.
That'd be great.
That would be wonderful, right? It'd be perfect, especially for Olivia because she's already celebrating Christmas, so she's got to start saving some money up, right, Olivia? All right. So we're in 3.1. That will get us ready for 3.1. We're just going to give you some definitions and a whole bunch of new postulates and theorems and stuff like that to make sure that you guys know how to use these. But I'm going to try this black marker. Let's see if it works. Actually, I'm going to use this one. So let's see if we run it up. All right, so the first thing that we're looking at today is, well, we're just doing some definitions. So two lines are parallel. Parallel lines they have to be coplanar and do not intersect. Parallel lines are coplanar and they do not intersect. All right. So if I have a line that is, let's label it AB, right? And we got another line, CD. These lines are on the same plane. How do I know they're on the same plane? Huh? Not because they're parallel?
Oh.
Well, I
They
mean,
don't
if they are parallel, yes, they have to be on the same plane. But I know they're on the same plane because I drew them on the same plane. Because the board is my plane, right? There's nowhere else for me to draw it. So the board represents my plane. And what does a plane do? It goes off in every direction, right? So it's infinite. Like a line does, just keeps going from end to end. And so I've got these two lines here. They do not intersect. I could make sure that you knew that if I drew this on if I drew this on a test or a quiz and I drew your lines like this, and then, like, how would I designate that these lines are parallel if I drew it on a quiz or a test? With arrows, right? So if I have arrows like this, I can put them anywhere on there. As long as I put arrows on there that are going in the same direction, then that tells you that those lines are parallel, right? How would I write, if I just wanted to say, if I wanted to say line AB is parallel to line CD, I would say, here's how I would identify AB as a line, right? You guys remember that? And CD would be identified as a line by the same thing. How do I say, what symbol do I use to say it's parallel? AB?
2 pipe symbols.
2 pipe symbols. So the pipe symbols on your keyboard are, what are they, over the one? No?
It's over the enter, I think.
Is it over the enter? On this one, it's over the backslash. So it may vary on your keyboard, but if you're wondering what the pipe symbol is, it just looks like that. Right? It looks like two straight lines, kind of like a capital I might look on your keyboard, but it's a little bit longer than the surrounding letters. So if you see that on a test or a quiz, that means AB is parallel to CD. Okay? Clear? Just making sure you understand the symbols that we use and what those symbols mean. Now this is a definition they give you in the book, and you don't use this one much, but lines that do not intersect but are not coplanar. So it's just like this, right? So I could say blank lines are not, and look, I'm going to give you guys a little practice on your symbols. Are not, check that out. I'm going to write it like that, right? Just to mess with you. Are not coplanar and do not intersect. They don't intersect, but it's just pointing out the fact that just because lines don't intersect doesn't mean that they're parallel. They have to be on the same plane. So we could have lines here. I could have a line going in the board, right, into that, on that plane there, that also doesn't intersect this line, but it wouldn't be coplanar. And so what we call those lines are skew lines. They're not parallel, but they're skew lines. And then two planes that don't intersect are parallel. I'm going to use my symbol, parallel planes. All right. So with lines, they could not intersect and not be parallel. They could simply be skewed. And just think about that. Like if this is my line, right? If this is my line and this is my lines are parallel. They don't intersect and they're in the same plane, all right? But if I do this, they still won't intersect, but now they're not in the same plane, so they're skew lines, right? But if it's a plane, see, I like that. I like that. I love to hear that sound. That's why I do my job. That's why it's so rewarding. But now with planes, if I use a piece of paper to represent my planes, right? And remember, this goes off in an infinite direction. If these guys are parallel like this, they're coplanar. But if I do anything else with them, right? If I shift this a little bit like this, or shift it a little bit like that, because they go off infinitely, and if I shift it like that, because they just keep going down, they're always going to cross somewhere. And so if they, as long as they don't intersect, then we know that for planes they're parallel. Okay? Does that make sense? Yes? Yes.
So for a line, couldn't I just, if they're not coplanar, this could be line and this could be line.
Right.
I could put it like this, but they still wouldn't intersect, so they'd still be skewed.
They would still be skewed, yeah, as long as they don't intersect. You're right. Yep. So he's saying they could be like this, right? And that's fine. I did it like that. It doesn't really matter. As long as they don't intersect, then they would be skew lines. Okay?
Got it.
All right. I'm giving you that definition, but I don't know if you will ever use that anywhere in your homework. I'm just telling you because they told us, right? Probably somewhere there'll be a problem that mentions something about skew, but I'll just say when I went through this material last year, I don't remember ever being on a test or, oh, you know what? Here it is. Problem number 20. Problem 20 says something about skew. So there you go. Let's talk about the parallel postulate. Because you guys like these postulates. Always get excited when I bring those up. Which one is the right one? Is this it? No, that's the weak one. So, the parallel postulate, and I'm kind of write down I have my own, so let me show you guys what I did last year when I was going through geometry, because I was tutoring somebody that was taking the class here. So I made my little notes, and these notes here, which were my nice little kind of concise versions of what I was going through in the book, which kind of corresponded to all the boxed off areas and all that kind of stuff. It was like, here's chapter 2. Chapter 2 starts here. And chapter 2 was kind of long, actually. Chapter 2 goes all the way down to there. But because I made notes as I went along, then it was really easy for me to take these notes and then write them onto a note card. Right? So I kind of had my own little concise, I'd already written in my own words. And so the cool thing about that now is that I can kind of teach from it this year. And so I'm just going to write down, what I'm going to write down for you, it may not match exactly what they're saying in the book, but it's kind of like, in my own words, here's my simplified way of stating this. All right? And so that's what you need to get good at also for your note cards, so you can fit as much information as possible on there. So parallel postulate says, this is postulate 13. I'll do P13. If there is a line, is a line and a point not on the line, there is exactly one line through that point parallel to the other. So one of the things that I do to kind of help make it a little more concise is not spelling out words that I can abbreviate, like PT for point, and making sure I use these symbols, right? And that'll also get me good at recognizing the symbols when I see them on a test, if I know what that represents a parallel line, right? And so pictures can also be useful. So if I have a point P, let me draw the point first. If I have a point P right here, and I have a line L, right? I know that there exists exactly one line that will pass through that point, and that is parallel to L. And you can, when you start thinking about it, all the lines I could draw through P, there's only one that I could draw, right? That would be parallel to my line L. So that's basically what that point postulate says. And there's another postulate, which is the perpendicular postulate. That's postulate 14. Perpendicular, whoops. And so for the perpendicular postulate, it basically says the same thing, but everywhere that you have parallel, you have perpendicular, which is actually just in one spot. It's like the same definition as that, but instead of there being a parallel right here, what's the symbol that I use for perpendicular? Yeah, Aiden?
It's like an upside down T.
Yeah, looks like this. It's a great way to describe it, right? Just looks like that. So that means perpendicular. So if you get good at recognizing the symbols, it won't take you as long to write this stuff either. So I could just say, same as parallel, but with perpendicular. However, it would be quick and easy for you to write that down. And so if we think about that again, we've got a point P, right? And we've got a line L. And there exists one line and only one line. No matter how many lines I draw through that point P, the only one that will actually give me a line that's perpendicular to L is that line right there, right? So there exists exactly one line that will satisfy that. And hopefully you guys all know when I say perpendicular, it means that they're going to form right angles, right? Or 90-degree angles. All right, any questions about those postulates or definitions? Good. I like it when you guys don't ask any questions. Good job, easy. We do have.
I have a question not about this.
Okay, what is it about the gingerbread though?
No.
Okay, what is it?
So,
Oh, did you need me to keep that up there?
oh no, not
Okay,
that.
all right,
No,
okay.
I just lost it for a second. I got it back.
All right, what is it?
Do we have 2 different sections this week, or do we only have 3.1? Or is it 3.1 and 3.2?
Yeah, we're gonna keep moving forward.
Okay.
Okay, is that all right? With your permission.
No.
Oh, that was a smart answer because it's like the rest of the kids in the class would be like, "What? You had your chance." I'm gonna overrule you and say yes, we are moving forward. All right. So I need to give you a couple more definitions, right? And this is how there's a bunch of definitions on page 131. So I kind of did a similar diagram to the one that they have there, and then wrote down my definitions based on that. So they've got a diagram that looks like this. They've labeled it 1, 2, 3, 4, 5, 6, 7, 8. And so a transversal, when we say a transversal, we mean a line is a line, I want to call it T in my diagram, that intersects two or more coplanar lines at different points. So this is what I label as T. This line here intersects these two coplanar lines here. How do I know those lines are coplanar? Aiden? Because I drew on the board, right? The board is my plane. And so it intersects both of those. And therefore the result is when you intersect two lines at different points, in other words, these lines, look like they're eventually going to intersect down here. I didn't draw the line to the point where they intersect. And it intersects them so two different points are created. And what happens is that it creates 8 different angles. You guys see that? So we're going to identify those angles. Corresponding angles, I'm going to use my little symbol for angles. Corresponding angles are angles 1 and 5. So 1 and 5 right here. Those would be corresponding. Also angle 3 and angle 7. Those would be corresponding. Who can tell me other angles that would be corresponding angles based on if 1 and 5 and 3 and 7 are corresponding, what else would be corresponding? Anybody that hasn't gotten their name on the board yet? Gabe?
2 and 6.
2 and 6, right? And what else, Gabe?
4 and 8.
4 and 8 also. So he's exactly right. 2 and 6, 2 and angle 6, and 4 and 8. So those are all of our corresponding angles. We also have something called alternate, exterior is first, alternate exterior angles. Alternate exterior angles would be angles 1 and 8. And there's one other set. If these are my alternate exterior, somebody else want to take a stab at what's my other alternate exterior angles on this diagram?
2 and 7.
2 and 7, right? So it's exterior. If you think about our drawing, these angles are on the outside of it, right? They're exterior. But they're not on the same side of those transversal, and so we call them alternate. These two are alternate exterior angles, and then 2 and 7. 2 and angle 7. Of course, that makes sense then that we would have alternate interior angles because we also have angles that look like they're on the interior of our diagram. And so like as you might expect, since these are the alternate exterior ones, then 3 and 6 would be the alternate interior, and 4 and 5 would be alternate interior angles. So angles 3 and angle 6, angle 4 and angle 5. And then finally, consecutive interior angles are angle 3 and angle 5. They're interior, but they're not alternating like the 3 and the 6 are. They're consecutive, so 3 and 5. They're right beside one another. Consecutive angles, and then also angles 4 and 6 would form consecutive interior angles. All right, any questions about those definitions? Yes?
Are there consecutive exterior angles?
So for, we don't have consecutive exterior angles. We don't call them that because they're not side by side. That's why we call them corresponding, right? They're on the same side of the transversal, just like the consecutive interior angles are. But since they're not side by side, we call them corresponding angles. Okay? All right, any other questions? So, what time did we start? We got 25 minutes? Is that correct?
It's at 2 o'clock.
Ends at 2, yeah, so we got 25 more. Hey, it's Miss Shannon. Hey, Miss Shannon. So we're in section 3.2. Let's scoot on over there, and we're going to do the proof of perpendicular lines. All right? Proof of perpendicular lines. We've given you some definitions regarding perpendicular lines. We said, like this one right here, if there is a point and a line exterior to that, if there's a point exterior to that line, then there exists exactly one line which is perpendicular. So we mentioned perpendicular stuff, but we're going to dig into that a little bit deeper now. And because you guys, it was so evident that you enjoyed proofs last time, that we want to make sure we cover those again. And give you another type of proof. So we've learned about 2-column proofs, and we've learned about paragraph proofs. And if that wasn't enough, we're going to learn about, what are they called, diagram proofs? Let's see, I wrote that down somewhere. Flow proofs. So it's kind of like a diagram, like a flow chart, if you've ever heard that term. Yeah, sounds great. Sounds great. All right, so let's talk about, there it is. That's our first definition, actually, a flow proof. So a flow proof uses arrows to show the flow of the logical argument as you're doing proofs now. So like if you look in the book on page 136, just to kind of make sure that we understand how flow proofs and paragraph proofs are related to one another, and 2-column proofs. They're all the same information, but just being displayed different ways, right? And so we may have even done this before. I don't know. We have this proof where we're given that angle 5 and angle 6 is a linear pair, that those two are linear pairs. What does linear pair mean?
They both make 180.
Makes sense.
Say that again?
They both make 180.
They both make 180. So if I have a line like this, and this line, let's do it at an angle. It doesn't look like it's perpendicular. Although that would be fine, but it looks like that, right? So angle 1 and angle 2 form a linear pair. And we could also just go ahead and extend this line all the way through. Angle 1 and 2 still form a linear pair, right? Don't get confused about that. If I draw some sort of wacky diagram that maybe it's a kite, right? I draw a kite like that, and I label this 1, 2, 3, 4. Recognize that 3 and 4 form a linear pair, right? However I draw this guy. If I said there's a string down here, right, then angle 5 and angle 6 created by the string form a linear pair, right? So I can draw all kinds of shapes and show you linear pairs, okay? You're probably going to have some problems with the book like that, so I want to make sure that that's clear to you. So any questions about that? Linear pairs? Yes?
Well, 1 and 3 typically be linear pairs.
Say that again?
1 and 3 typically be linear.
Yeah, they're linear pairs as well. 1 and 2 are linear pairs. Good question. And that's exactly right. All right. And those are all coplanar lines. Why?
Because they're on the same
So I drew them on the board, right? The board is my plane. If I draw it on your paper, they're all coplanar because the paper is your plane, right? All right, so don't get confused by the plane thing. I just want to make sure everybody's got that. So see right here, they tell us these couple of angles are linear pairs, and they want us to prove, they said 5 and 6 and 6 and 7 are both linear pairs. They want to prove that 5 and 7 are congruent angles. Now, we know they're congruent angles because we have our vertical angles theorem, right? Don't we have some theorem like that or postulate like that? Didn't we learn something like that last chapter?
We got
Right.
vertical angle.
What was it called?
Definition of vertical pairs.
Definition?
Vertical angle.
So I'm gonna take out my notes.
Vertical angle postulation.
The vertical, let's see what it was. I can tell you.
I think it's a theorem.
That's a theorem.
Vertical angle theorem.
Let's see. I'm gonna guess it's a theorem too. But I'm having trouble finding that. Two planes vertical, where are you? Negation, nope, none of that. Vertical angles. It's just a definition. The definition of vertical angles have sides that form two pairs of opposite rays. So we actually learned about that in chapter number 1. So we learned about a linear pair, we learned about vertical angles, but we did have a theorem, right, somewhere.
Yeah,
Mine
in
says
chapter 2.
Vertical angles are from 2.6. Theorem 2.6.
Oh, 2.6.
My definition says vertical angles are congruent.
Mm-hmm.
I see it. All right, vertical angles theorem. That's it, right? Theorem 2.6. Very good. It was on the back side of the page, so that's why I couldn't find it. All right, so good job. Way to track that. Yeah, again, that was a test for you guys. I knew the answer all along.
Yeah.
Yeah, I didn't appreciate sarcasm in that remark there.
What's the trouble?
So we already know that, right? But we're proving that that's so, and so they've got a 2-column proof listed there on page 136, where we give the fact that they're linear pair, right? That's given, and then because of that, because of the linear pair postulate, then we can say that they're supplementary. And because of the congruent supplements theorem, if we know that 5 and 6 are supplementary and 6 and 7 are supplementary, the congruent supplements theorem says that if two different angles are supplementary to the same angle, then those two angles have to be congruent, right? And so that's what the congruent supplements theorem tells you, and that proves point number 3. All right. So there's the 2-column proof. That's my favorite kind of proof. But they're really all the same. It's just, to me, that's the most nice, concise way of doing it. It's easy to see, right? Paragraph proof is wordy, right? That's what you would do in writing class. You're just stating all of that in plain English, writing it out in a paragraph form. The flow proof, you see how that does? You got the givens that are there, and then you got arrows that take you from the given to the next statements. Because in our 2-column proof, where we say angle 5 and 6 are a linear pair in statement 1, well, that really directly corresponds to angle 5 and 6 are supplementary in statement 2, right? So that's why we have boxes there that correspond to each of those sections. And then they come together at the end and they say the angle 5 is congruent with angle 7. That's the congruent supplements theorem. So you probably have some homework problems that give you an opportunity to try this. If I give it to you on a test, again, it's going to be a fill-in-the-blank sort of thing, right? So I'll kind of draw out that for you, and you'll have to put the appropriate information in there. But honestly, what's most important to me is that you guys know how to do the 2-column one, because I think it's kind of easy to transfer the 2-column one to the other ones. Yes?
So on our test, they will be fill in the blank, or will you have us make a?
Like, will I make you do a whole one?
Uh-huh.
You know, it just depends on how much coffee I've had, probably. If I'm doing it in the morning and I haven't had much coffee, you're going to have to do all the proofs all by yourself. But so hopefully I've had some coffee by the time I do it. They're probably going to be fill in the blank.
Okay.
All right? If I gave you one where you had to do the whole thing, it'd be a super simple one. All right?
Okay.
If there's going to be more than 3 steps in there, then I'm going to give you the pieces of information to fill in the blank. Okay? All right. Did you have one on this last quiz? You did?
No.
Okay. So you do, yeah, you have one on the test. I was like, I know I just saw one. And so on the test, it is fill in the blank. But some of it, I may give you a part of the statement, and you have to fill in the missing part of, like, for the reason, for example, right? I might say the blank postulate, and you got to tell me it's the linear pair postulate or something like that. Okay? Sound good? All right. But of course, I would have given you, I would have made the conclusion on the left side, said we're concluding that this took place, and then you just tell me the reason for that. I need to do it this way, since that's how it will look like you guys. This is what I give you, and you give me the reason. Okay? All right, so let's talk about theorems 3.1, 3.2, and 3.3. If 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Why is that so? Theorem 3.1, Theorem 3.1. If two lines intersect to form a linear pair of, I'm going to write congruent like that, of congruent angles. I'm going to write angles like that, right? Just trying to use some shorthand notation so it will take up as much space. If two lines intersect to form a linear pair of congruent angles, the lines are perpendicular. And that should make sense to us. Got a little drawing here. This is line G, this is line H, and I can say G is perpendicular to H. So, if you look at my drawing, what is this curvy line here and that curvy line there? What does that mean as they are related to one another? Let's see if somebody that's not on the board can tell me that. Are you on the board, Olivia?
I'm not.
All right, what does mean?
This is probably a dumb assumption.
Okay, let's hear it. Let's hear it. I love dumb assumptions.
I don't know the perfect words for it, but I'm just
Okay.
gonna try to explain it. Is it like the complement and the supplement and the angle, like the smaller bit, like?
Well, okay, that's a good guess. That's a good guess. It's
is one smaller than the other, or something?
They're not. They're not. And the these are definitely, what would these angles be based on what you just said? A complement or supplements of one another?
You mean like, is it like a complement or?
Like, is this angle and this angle, are these angles supplements or are these angles complements?
Supplement?
Supplements, because when you add them up, you get 180 degrees, right? So you got your name on the board. Way to give it a shot. The fact that I drew one smaller than the other really doesn't have any bearing on it. I could totally do it like this, and it would still be telling you the same thing. The only reason I'm drawing them different sizes is so that you realize that they're not connected, that I'm proving something else about those. Somebody else that doesn't have their name on the board, can anybody else tell me what I'm proving? I know some of you guys are like, oh, pick me, I know. Joshua, your name is on the board though, right? But no one else is answering. So what is it, Joshua?
Are you saying that they're different angles?
I'm not. What am I saying? What am I saying, Camille?
That they're the same.
I'm saying they're the same angles. Now, if they were different angles, and the reason I'm saying they're the same is because my curved line is only one curved line. Okay? If I'd done it like this, where there were two curved lines here and only one curved line on the other side, I would be saying that they're different angles. All right? That's just like if I draw a triangle here, like this, if I do a tick on each of those, I'm saying that those lengths are the same. All right? But if I do two ticks on this one, I'm saying the length of that one is different. All right? So also, if I want to let you know that these two angles here are the same, I would draw a single line here and a single line there. But if I want you to know that this angle is different in size, I would draw two lines there. Okay? So that's what the curved lines mean. If there's one, everywhere you see the one curved line, you know all of those angles are equal. Okay? Does that make sense? All right, it's just, again, just making sure you understand. If you see it on a test, you're like, he drew one line, I know that those angles are equal to one another. All right? So how does that, what bearing does that have on this definition that, or this theorem that we've just stated? Well, if both of those angles are equal, right? And if both angles are equal, and as Olivia already rightly told us, we know they're supplementary because this line here is coming off, it forms a linear pair, so we know these two angles equal 180. So two equal angles that total up to be 180, the individual angles must be?
Supplementary.
What must the measurement of those angles be?
100.
No, the individual
90.
angle.
Oh,
It's got to
90.
be 90 because only 90 plus 90 is going to give me 180, right? And so if they form a linear pair, then the lines have to be perpendicular because both of these angles have to be 90 degrees, right? Make sense? So I'm just talking through the theorem, but in talking through this theorem, I want to make sure you understand the symbols. A single curved line, and then there's another single curved line on the angle. It means that those angles are the same. If I've drawn this triangle like this, that tells you that all of the angles are different angles. Okay? If I had drawn those two like that, and then had done this right here, and you look at that and go, that's got to be the same angle as that, you cannot make that assumption. Because I didn't write anything down to indicate that. So your assumption has to be, that one's different. All right? Unless you can prove otherwise based on other information in the problem. And the reason I'm saying that is because as we continue to do these proofs throughout the years, yeah, I'm keeping you guys, I love you guys so much, I'm going to have you for the next 3 years. Congratulations. But if we're doing a proof later in the year, you know, I might give you a picture like this and you cannot assume that that angle's the same. Right? You have to prove that to me in the proof. Okay? All right. Let's move on to theorem 3.2. Theorem 3.2. That says that if two sides of two adjacent acute angles, two things we need to know there. What's an adjacent angle?
They're right next to.
They're right next to one another. They share a side, right? If they're acute angles, what does that mean? Less than 90 degrees. That's right. Less than 90 degrees. If two sides of two adjacent angles are perpendicular, the angles are complementary. Okay? So we have something like this. They are there are two adjacent angles, angle 1 and angle 2 right here. We know that if the two sides, the two other sides of the adjacent angles form a 90-degree angle, they're perpendicular, then we also know that these angles are complementary, right? In other words, they have to total up to 90 degrees. That's kind of an obvious one, right? Should be pretty straightforward. And then finally, theorem 3.3 says if two lines are perpendicular, then they intersect to form four right angles. So if I have two lines like this, and I'm told that those lines are perpendicular, then I know they will form four right angles. Again, this is just information that's going to help you be able to prove, to write proofs for other problems, right? If you know, if you've got these theorems in your arsenal. So this is the kind of stuff that you'll be able to write down for. I give you two lines that I tell you they're perpendicular. You'll be able to say, oh, well, they're right angles. And then by the definition of right angles, then I know that those angles are 90 degrees, right? There's things like that where you can just kind of chain these things together and establish your proof. All right, so it's more definitions today. But do these three theorems make sense to everybody? Make clear? All right, you guys, I really wanted to get through chapter 3.3, so you did a good job of stalling me long enough. Wait a minute. Oh, wait a minute. You guys, we actually have 7 more minutes before your next class. Is that correct? Oh, I don't have time for this. Yeah, I don't have time for that. Sorry. All right, yeah, you guys are saying. Darn.
So does that mean we don't have to do 3.3?
You won't have to do 3.3 homework. Yep, just 3.1 and 3.2. All right, you guys have a good day.